Hi guys, this video is going to cover torque, one of the very important areas in our study of basic physics. Torque as a whole can be looked at as the rotational version of force. So you can think of force and torque being somewhat analogous in ways. Now they are definitely not the same thing, but they do have a lot of similarities. Oftentimes you will see torque referred to as the rotational analog of force, which basically just means that torque is analogous to force in rotational motion. So when I'm saying rotational motion, I'm talking about basically spinning or turning something. Like your car is able to turn the wheels of the crankshaft, the engine is able to turn the crankshaft. You turn the wheel, the steering wheel of your car. If you spin a basketball, that is employing some torque. Anything where something is caused to rotate requires some sort of understanding and some use of the model for torque. And in this video, we're going to do a basic sort of layout of some of the ideas of torque by constructing a conceptual model from our experience, then creating a mathematical model with some graphing and algebra, and then we're going to see if we can apply it through different systems, and we're going to focus primarily in this video, once we've set up the equation, in what we call a balance of torques. Just like a balance of force, and if you think about what that meant, you can kind of maybe start to understand what a balance of torques will do. In this video, what I'd like you to do is try to take notes along with it. Pause it where you need to, and write out anything that you feel is very important. Oftentimes, if you come up with a question while the video is playing, pause and write down that question so that you can ask your teacher in class, or you can look it up again later. This will be covered in the Rube Goldberg project that we do later on in the semester. So let's get started. So I have here a door, and to me, this is one of the most obvious examples of torque. You push on the door, and it rotates. Now I'm going to ask you a series of questions. I want you to think about them, and I'm not going to leave very much time in the video, so try to pause after each question to think about it yourself. Jot down what you think is happening. So when I push the door, first question is, where do I usually push? Where's the most common place you push? I oftentimes notice that the place where most people push is where the door is starting to wear away. And if you look at that around schools or gyms or places where lots of people go, you'll kind of see the most common place to push. So think about that for a sec and mark that down on a little sketch of a door. If you're observant of such things, you probably notice that you push somewhere around the handle, sometimes below, sometimes above, and sometimes on the handle. Some tall people might even push all the way up here, right? But what's common about this is that all the pushing has happened over here in this region. How could you describe that region in respect to the door's shape? So try to find a way to describe that region in respect to the door's shape and its parts. Pause the video if you need to, take some time. So perhaps you said somewhere near the handle of the door, and that is true, but let's take a look and see if we can go a little bit deeper. After all, we are talking about rotation. So I might describe that place where all the X's are as the distance away from wherever the door is rotating around, or the hinges. And the hinges tend to be on the opposite side to the handle. So somewhere along this line right here, we have the hinges of the door. So I can think about that in terms of the hinges, not only the handle. Now, does it matter how high you push? Do you have to push higher or lower to get a different kind of rotation? Think about that for a sec. Pause the video if you need to. Well, I'll look into that a little bit later. Perhaps right now you see that there's no correlation between how high you push, only how far away you push from the axes. Or you may have noticed that it's harder to push the door from higher up or lower, and it's easier to push right in the middle. We'll kind of look at why that might be a little bit later in this video. So far, we are trying to describe, let's kind of look back to the goal, we're trying to describe how something rotates, right? So maybe we need to come up with a little bit of a definition for torque, just so that we have some words to use. And what I'm going to call torque, from the introduction that I gave you a few minutes ago, I'm going to call torque the ability of a force to cause the rotation, right? So it's almost like how easy is it for the door to move? If we have high torque, what does that mean compared to low torque? If something has high torque, I might say, and this is just all speculation right now, that the door will rotate more easily or at its maximum sort of rotation ability. Whereas if the torque was low, I might say that the door doesn't rotate very easily. Think about this in terms of those truck commercials that you hear, or if you have a truck yourself, they oftentimes talk about the torque that the truck has. And do you want high torque or low torque? Kind of think about that. Okay, so right now we're going to define torque as, and I'm going to write it over here, the ability, and this is just my working definition, the ability of a force to rotate an object. So if I have high torque, I have high ability. If I have low torque, I have low ability, right? Now this isn't the end of the discussion. This is just the beginning. So far, what's going to affect that ability? What's going to affect the ability of the force? Did you notice that you very seldom push over here to open a door? You definitely don't push all the way down here, right? If you pushed over there, it would be a lot more difficult, if you've ever done it, to actually push the door open or rotate it the same amount that you would if you put it over here. Maybe there's a reason that handles are on the outside, and it's not just aesthetics, right? The hobbits in The Lord of the Rings seemed to do things a little differently and had the doorknobs in the middle of the door, which isn't the most useful, as you can imagine. So let's sort of define a variable here. Let's call torque this Greek letter tau, and the only reason I'm telling you to use this is because that's what's most generally used, but you could use any letter you wanted. It kind of just looks like a fancy T, but that's how I'm going to describe torque when I write it mathematically. So conceptually speaking, in terms of where you push on a door, what allows you to have more ability to rotate the door? Pause the video and think about that. I'll ask the question again. In terms of torque, which is the ability to rotate, in this case, the door, how does where you push relate to your torque, or the torque that you can sort of provide for the door? So if you had a second to pause and think about that, you might have come up with that torque is greater, or your ability to rotate the door is greater when you push further away from the hinges. Let's generalize that a little more and think about maybe a basketball. So I'm going to just draw a little basketball over here. And think about how you get that basketball to spin. When you spin it, say on the ground, where does it spin around? It spins around maybe this axis right here, right? So it will sort of turn like so and kind of keep spinning. But it's spinning around that central axis. So if we think about this, we might call this maybe significant. What is that axis in the door example? You probably guessed the hinges, right? Well, we're going to call that in general an axis of rotation. And an axis of rotation is now a more general term that doesn't only apply to the door, that describes the location that the object rotates around. So that's an important definition. The axis of rotation is the location, or the axis, around which the object rotates. So for the door, it's the hinges. For the basketball, it's this imaginary sort of line that passes through the basketball. Think about some other things. For a wheel, where would that be? In the center of the wheel, where it turns around, right? So anywhere you would call the axis of rotation is the place around which the object rotates. That's a really important way to describe the hinges of the door. So now I might say for my conceptual model that my ability to rotate the object, or my torque, is greater when I push further away from the axis of rotation. I would be comfortable with that. So let me say, let me make this a little smaller here so we have a little more space, and I'm going to write a proportion. So I'm going to say torque is directly proportional to the distance from where I push. And I'm going to call that distance R. Now, you may have noticed the sort of trend here with these little proportionality statements is that when both variables are in the numerator, that implies that they have a direct relationship. There's no exponents, no fractions, nothing else. So that means when R goes up, torque will go up, R being the distance away from the axis of rotation. So when I push further away from the axis of rotation, the torque is more. Now they're not equal because the number of how far away you push, and most standard doors are probably about 2.5 feet wide. When you push about 2.5 feet from the axis of rotation, that doesn't mean you have 2.5 units of torque, right? But they are proportional to each other. So we kind of have that one variable down for our conceptual model. I think most of you came up with that in the very beginning. If I push further away from the hinges, I have more ability to rotate the door. What other variables might affect the rotation of the door? So think about some other things that would make the door have a greater ability to rotate or less ability to rotate. Pause the video and think about that for a second. So maybe you came up with something. One thing I was thinking about is maybe how hard I push. If you've ever been mad and slammed a door, you know that you push harder than when you sort of more gently close it as you're slipping out of a meeting or class to go to the restroom. So you can think of that, right? And now describe it in terms of the proportionality statement. What would make for a higher torque in terms of force? Well, a greater force means that the door rotates more. It has a greater ability to rotate. So what I'm going to say then, I'm going to put this in a different color, is that the torque is perhaps proportional to the amount of force that I apply. If I apply more force, I'll have more torque. This relates very closely to those sort of truck commercials where they describe the torque of the truck, right? The amount of push that the engine has the ability to rotate the crankshaft, which turns the wheels. And that's a simplified version of explanation, but basically covers the idea. So right here we have two proportions. We have torque is proportional to distance from the axis of rotation, in this case the hinges, and torque is proportional to how hard you push, or the force. Now the problem is we don't know if there's a quadratic relationship here, or a cubic relationship, or something weird where they're not just sort of a direct one-to-one relationship. So let's go now into the mathematical model. What I would suggest doing right now is pausing the video and restating everything we have talked about so far in as few sentences as possible. This is a really good way to study to see if you understand what you've just heard. If you can't explain it, then you need to revisit it again until you do understand and can recall it from memory without looking at your notes. Okay, so now we have two basic variables that might affect torque, and what we're going to do now, our goal is to build a mathematical model, not just a conceptual one, in order to predict the amount of torque an object experiences. Oh, we got a typo there. And then in order to do that, we're going to set up just our little mathematical model diagram so that we can kind of visualize where the variables fit into the process if we were going to do this in an experiment. So I'm going to draw up my mathematical model diagram. And basically this box is my mathematical model machine, right? And I want to put some variable into it and get out what? So what is the output variable? What we generally in science call the dependent variable. Well, if we design our experiment right, it should be torque, right? Because that's what we're trying to predict. We want to know how will the output be torque, all right? The input then is your independent variable. Now there could be more than one independent variable, so we have to be careful that we pick one to start with to do an experiment and hold the other one constant or the others constant until we're ready to test one of the other variables. So what are possible input variables? Pause the video and think about that for a sec. Well, you probably think about what we just discussed on the last slide, and that was that possible inputs could be force or distance, and not just any distance, but the distance from the axis of rotation. Now, I'm just writing distance here because I'm running out of room, but we want the distance from the axis of rotation. So there we have our basic model. Now, at this point, what I need to do is, and this is what we do on the tests in the model building section and what we do in the labs a lot of the time, is we go straight to our graph and we say, torque's my output, so that's my dependent variable, so it's going to go here. And on my x-axis, or my horizontal axis, my input axis, I'm going to pick one of those to start with. How about we start with force? So I'm going to put force over here. And I know the units of force already, and I don't know the units of torque, so it's okay to leave them off right now. And I'm going to title my graph already, torque versus force, y versus x. Now right there, if this were a test, I've already accumulated some points without even having been able to do calculations yet, which can be helpful for some people that struggle more with math. But let's kind of look at this now and see if we can actually get a relationship for torque versus force. What will we have to hold constant? So I'm going to make my list of constants over here. So in the experiment of force and how that affects torque, so we're not looking at distance right now, what do I need to hold constant? So let's think of the door example. I push on the door and I have a torque sensor or a torque transducer in order to measure the rotational ability of the door. Yes, there is such a thing. I can also use a force sensor, which will determine how hard I'm pushing on the door. What do I have to hold constant, though, in that experiment so I don't interrupt my results? Think about that for a sec. Yep, hopefully you guessed it right. The constant is going to have to be, in this case, distance. And hopefully there's nothing else. But one of the other things we could say that's sort of more conceptual thing is that we can't be going between different doors for every sort of step of the process. We could do the same experiment on a variety of different doors to kind of compare if it's the same across all kinds of doors. But for right now, with this just basic measurements, we're going to try to hold the distance constant. At this point, you'd write your procedure, right? And the procedure, a lot of people sort of go down the wrong path on. And here's a nice, easy model to help guide your procedure. How are you going to measure this? Torque. How are you going to measure this? Force. And how are you going to hold this constant? That's basically what the procedure is having us describe. Now, obviously, in more detail, so that if someone were to look at it again, or if you were to look back, you could kind of see what you did and make any modifications necessary. So now that we know that we put force on our x-axis, torque on our y-axis, and we are going to try to hold distance constant, let's collect some data. Now, I'm going to use a torque sensor that will fit into the hinge and tell me the rotational ability of the door. Now, I'm being very vague on that because how it measures that is beyond the scope of this video, but it does. It can tell us a number for how much torque the door has on a particular push. And then I'm going to use a force sensor, which is basically a sensor that allows you to, so you would use it almost like your hand, so it's a little plate, and you push with it, and it tells you how hard you're pushing, which is basically just like a bathroom scale that's sideways. All right, and it will tell you how much you're pushing with. And on the next slide, I'm going to show you some data that I collected with that so that we can graph it and see what this mathematical relationship would be. Okay, so here I have a prettier graph than those messy sketches, and I have torque again in units unknown right now and force in newtons, and this is a torque versus force graph and relationship. And on the right hand side I have some data that I collected. So I try to keep the forces clean as possible in easy increments, and I pushed with 10 newtons of force, then 20, then 30, then 40, then 50. If you're thinking about experimental design, another cool way you could control that is by using a spring, right? And every time you just sort of push the spring back, compress it a little bit more so it can push harder, and that might keep the force very consistent. And then I used the torque transducer, and I got these values of torque, once again units unknown. So maybe I'll make my increments go up in fives, and so let's say on this axis each of these little blocks is worth 5 units, and then on the other axis I'm going to use 5 as well. Okay, so when it's 10 it's 7.6, so that's somewhere around here. All right, then when it's 20 it's 15.2. Let's see, we're going to just squeeze it in here, so we have 10, 15, 20, somewhere about here, and you get the point. So I'm going to pause here and finish graphing this, and then we'll look at what happens. Okay, so I graphed the rest of the points. It's really messy, but we get the gist. And we see there, very nicely, we have, let's add a best fit line. Okay, that's reasonable, not great. But there we have a nice sort of direct linear shape. All right, very cool. So then let's try to write out what we would do to kind of make the model. Now we see that this is this general shape, y equals mx. Now the b looks like it's 0 from my trend line, so I'm going to leave that off. Now I'm going to replace the variables. So y becomes tau for torque, and x becomes f for force. And that's just literally taken from my graph, right? And then the slope here I can calculate, and I see if I use 2 points that fall on the line, right? Remember, they're not necessarily data points. In this case, because I sort of picked perfect data, we could use 2 data points. Let's see. I calculate a slope of 0.76. And if I were doing this on Excel, which I did before, I found that my r-squared value is 1. So that's a pretty good fit. And there's no y-intercept, and I don't expect there to be any. If I'm not pushing the door, if x is 0 or if force is 0, then I shouldn't really have any torque. So that's great. All right. So that shows very little to actually no error in this case. So I have a little function here. Okay. Let's see the other one now, the other relationship. So if we went back to the other slide, we could pick out what that would be. So I'll go ahead and type it on here. If you take a second and look back at the little mathematical model diagram and try to figure out what the other relationship we're testing would be and what the constant would be in that case. Okay, so there you go. We've got distance from the axis of rotation now is our variable that we are trying to manipulate, and we're going to see how that registers on the torque sensor. So we've got a torque versus distance graph. Now I didn't put distance from the axis of rotation because of space, but that's really what it is. And then I have the data up here in the top right hand corner. I varied the distance about 10 centimeters every time I changed it, and I registered what was on the torque sensor. Now, in order to just save time, I'm not going to really graph the whole thing, but I did graph it on Excel, and I got a really nice line that looked like this. And so, once again, we have this sort of direct relationship. So I'm going to try to kind of find some space here. Maybe move this data up to make some room. And it looks like I have the same thing again. Y equals mx plus 0, f, or y being torque, x being now distance, and I'm going to use r like I did on the previous pages. And then I have to find the slope. Numerically, I did, again, use 2 points, and I found that the slope was 30. All right, so I have torque equals 30 times r. And then I have on the left there, torque equals 0.76 times f. Now the game becomes, what does the slope mean? And a lot of times on a test, people think that that's such a hard question. Like, how would you even know if it's some concept you haven't seen? Well, as I've been saying a lot of times in class, that little mathematical model diagram is very helpful, because we see there very clearly that our input is on the x-axis, or the horizontal axis, and our output is the y variable. So if you hold something constant, then where do constants show up mathematically? Well, in whatever the function is, in that constant parameter of the function. Now, sometimes it's not as simple as just saying, oh, if I held distance constant, then the constant is distance in the equation. Sometimes it is that easy, but sometimes it's not. Sometimes it can be 1 over distance, or some other sort of combination of things. But let's look over here for a second. On the left-hand side, when we studied torque versus force, what did we hold constant? Go back and look in your notes, and you should see that we held the distance from the axis of rotation constant. Because if we changed how hard we pushed and how far we pushed from the rotation point, then we wouldn't know what's really affecting the torque. It would be hard to sort of parcel that out. But here we know that we held that constant, and that is the length of the width of the door, where the door handle was. It's 0.76 meters away from the axis of rotation. Now let's make sure that that could really be, so if we want to make this sort of more generic, that would mean that I would have to replace that with r, and then I could leave f there, so I'd have torque equals distance times force. Okay, let's look at the other one. Here, what did I hold constant for this relationship? So I changed the distance every time to see how the torque would respond, and then I had to not push harder any other time or less, so I had to keep the same constant force. So this slope here must have something to do with force. So torque equals force times distance. Do both of those equations say the same thing? If yes, which they do, then that's the function. But if they don't, then I have to try to combine them in another way, and we'll leave that for another time. But this is kind of cool. So we've got here a function, a mathematical model, that could predict the amount of torque that the door sort of experiences based on the product of the force you push with and how far away you push from the axis of rotations. I think that's pretty cool. And it shows from our data. We didn't make this up, right? Let's do a little last thing here before we move along, and let's figure out what the units of torque might be. So remember, we can get units by looking at what sort of other things fall into the equation. So if force is measured in newtons and distance is measured in meters, then the unit of torque is a newton meter. And that is correct. A newton times a meter, or a newton meter, is torque. Alright, so that's the unit. So now I could add this to my graph, a newton times a meter. It's not a nanometer, right? That would be a little n, but a newton meter. So I'd add it here as well. Alright, so at this point, if you haven't really caught the basics, or if something's really confusing you, go back and try to figure out where it is. Because what we're about to do next is kind of move to a little bit of a deeper sort of level of what torque is, and we're going to consider if something else might also affect it that might be missing from our equation. Okay, so I'm back to my door example again. Just FYI, kind of on a side note, whenever you're trying to come up with a new sort of equation, you're in a lab or you're doing like a thought experiment, trying to theoretically come up with, predict some sort of variable, it's often useful to have a go-to example. And for me, torque is a door because it's very, very clear, I think, and it's common to our everyday experience. So we've established this distance right here is R, how hard we push is F, right? And both the product of those two things, let me switch colors here, the product of those two things gives me how much torque the door has, or how much ability it has. So that's great. But there's one little thing missing that we didn't consider, and this oftentimes happens when you're building a model. Your first model is just preliminary. There might be something either incorrect in it, or it's just not complete yet. So remember when I asked you to consider if pushing up here or down here would affect how the door rotates. Now, directly pushing up there wouldn't really affect, but if you're not super tall, almost 2 meters tall, it would be hard to push up here at this spot that I'm outlining in blue. So your arm, so I'm going to draw this kind of from a side view here. If this is the door from the side, and you're standing over here, your arm would have to reach up like this, and you wouldn't be able to push directly on, right? You wouldn't be able to push straight ahead like this, which would mean that you can't get your full sort of push behind you. So then we have to consider how that might affect the rotation of the door. Now in this example, it's a little silly, but there's some cases where it becomes very, very important on how you open or how you rotate something. So here what's going to be important is this force right here, your applied force, is making this little angle with the door. Now if we think of forces from last year, try to consider now when you have an angled force against something or pushing something, what happens or how do we analyze that force? What can we do to analyze how the object's going to move as a result of that force that's not head on or at 90 degrees to the surface, but that's sort of at an angle? So pause the video, kind of think back, and the question once again is, when a force is applied at an angle, how do we analyze how that force is interacting with the object? Take a second or so. Hopefully you remembered that when I push at an angle like this, I have an x component and I have a y component to that push, right? So what's going to rotate the door? Is this vertical component contributing to the rotation of the door? Hopefully you can see that it's not, right? Because it's not actually pushing the door into sort of that dimension that the x component is pushing it into. Does it rotate up along the door? No. It rotates sort of into the door if you think about it, right? So you push into the door in a sense, and it pushes through that same dimension. So this y component, or this vertical component, if we want to be more generic, has nothing to do with the amount of torque. So right now what you've done is you've actually not used your full force to push the door. You're only using the x component of your force to push the door in this case. Now let's be careful here and not use the terms x and y anymore. Let's try to use this as being the opposite side to the angle and this being the adjacent side to the angle, if the angle is measured between the force and the door, where I've drawn the little theta. So which side matters in terms of opposite or adjacent? Good. Hopefully you got the opposite side matters. So let's figure out what that would be. So if we want to use some trigonometry here, we could say that if I'm trying to find the opposite side, I'm going to say that the sine of that angle is equal to the opposite side over the hypotenuse, which is the force, right? So my full force is the hypotenuse. That's like my arm right here. That's this applied force. So I'm going to say the opposite side is the x component, or it's going to actually be the perpendicular component to the door, right? Because it's perpendicular to the door's surface, over the total force. So if I solve for that perpendicular component, it becomes, I multiply by f, it becomes f sine of theta. So what this really should be in my equation over here, and I'll come do it in a different color so you can see it, okay, is that this should really be the perpendicular component of the force, right, times the distance from the axis of rotation. Now, if you're pushing straight on, do you have to even worry about that? Heck no. All you need to care about is how hard you're pushing. But if you're not pushing head on and you've got a little bit of an angle, then you need to first find the perpendicular component to the door, which in our terms here, if you look at it, is that opposite side to the angle between the force and the door. And it would always be that angle, right? Unless they give you a different angle. So the equation would really become then torque equals Fr sine theta. The sine theta in my case here is attached to the F. So that is the more complete version of the torque equation. And so you can kind of go back and look at it again to see how we constructed that model and really understand that. All right, so let's look at just a few really quick applications so that you can be done with this assignment and move on to better and greater things. All right, so here we have a seesaw, and we're going to practice here a really important concept that is called balancing torque. Now, the video about levers that you're going to watch will help sort of flesh this out a lot more and give more details about different kinds of torque applications through different levers. Because after all, this board is rotating around this axis of rotation. We oftentimes call this a pivot or a fulcrum. Pivot or a fulcrum. That's the point around which that plank of wood or metal or whatever is rotating. Because if you imagine it, the kids would rotate back and forth like this around that point, right? So let's now use some variables and terminology that we've come up with. So remember that the force here for this kid is his weight, right? That's the force he's applying to the seesaw. And this kid's weight is also applying to the seesaw. Now we treat them as two different forces pushing some distance from the axis of rotation, which we deemed was R. So we have that one, and we also have this side. So really here, this seesaw is experiencing two torques at the same time. Now if the person on the left, let's name them person A, okay, person A is heavier, then we know from our experience that the seesaw will tip that way. If they're both exactly the same weight, what would you expect to happen? Good. You'd expect them to be balanced. Person B and person A. So if they're exactly the same mg on both sides, and they're sitting the same distance from both sides, then the torque from person A should be the same as the torque from person B. Now, are they pushing, if you were to look at this seesaw and imagine that if I push down on B here, the whole thing would rotate like this. Right? If I kept pushing on B, you could kind of swing it all the way around. Now, obviously, it doesn't do that because it's sitting on the ground. The ground would stop it. But if it wasn't, it could be like sort of an imaginary floating seesaw that could spin all the way around. So if I'm pushing down on B this way, and you're pushing down on A on this side, are we pushing both clockwise, or is one of us pushing the opposite direction? Well, I'm pushing clockwise and the other person's pushing counterclockwise, because if you imagine it, person A would make it go this way, and person B is clearly making it go this way. So we're balancing each other out. So our torques could sum torque A plus torque B, or A minus torque B, because they're pushing opposite directions, should sum to 0. And because they sum, so this is a negative, because they sum to 0, they're equal to each other, just like with force. So now I can write FR for object A on their side equals FR for object B on the other side. So I've just substituted in their weight, their force of weight, the FB or the FA, MGA or MGB, and their distance, RA or RB, from the axis of rotation. So now you might be able to see what's really cool here is that if one person has a much bigger mass, how could you still keep the whole system balanced? How could you still make each torque equal? Think about that for a sec. Hopefully you notice that if F is really big here and F is much smaller here, then in order for these two quantities to be equal, if this is really big, then that's got to be small to balance out this very small one and this big distance. So basically, if you want to balance out two people on a seesaw, the heavier person has to move closer in. They have to have a smaller distance from the axis of rotation, and they'll be able to balance. Now, there might become a point where there isn't enough distance to balance the seesaw if one person is much heavier or denser than the other, and that would have a need to make the seesaw longer. All right, so watch this example again and think of some other applications. We have wrenches, different kinds of levers and lifts. Your elbow, right, is an example of a kind of lever that's using torque. The wheels on your car turning, all different kinds of things. A fan spinning. There's many different applications. On the next slide, I'm going to have some practice questions. I will work one of them, and then you are to complete the worksheet that you have as a supplement to this video, and you will use it later on when you're building, in your project. Okay, so here's the one example problem that I'm going to work. A fisherman hangs two fish on his fishing rod, which is suspended over a rock, creating a fulcrum. If one fish is 2 kilograms and is 0.7 meters from the rock, and the other fish is 3 kilograms, how far from the rock should he hang the 3 kilogram fish to balance the system? Okay, so I know some people have maybe a hard time on tests trying to understand questions, for whatever reason. So what you should always do is try to draw a little picture that helps. So here's his fishing pole, and here's the rock that has created a fulcrum. So we use context clues. We know we're studying torque, and we're trying to do a balance here, so we know that it has to look something like this. It can't be something else, all right, in the context of what we're learning. So then we're going to put the 2 kilogram fish over here. So I'm going to label that. And I'm going to also label the distance from the rock, which is 0.7 meters. And then I'm going to put this 3 kilogram fish kind of just randomly out here. I don't know where. And I know that I'm trying to find this distance R over here. So I'm going to say that the torque of the 2 kilogram fish needs to be the same that the torque of the 3 kilogram fish, right? The torque that the 3 kilogram fish provides, I should say, needs to be the same as the 2 kilogram. So I know that torque is equal to F times R times sine theta, and the same on this side. So I'm going to just subscript these so we can keep track, okay? Now the force, we have to figure out what force is actually being applied here. Well, it's really the fish's mass times gravity, right? So it's weight. So I'm going to put M 2 times g times r2 equals m3 times g times r3. All right, so the 2 kilogram fish times the acceleration due to gravity, I'm just using 10 here for ease, times 0.7 equals the 3 kilogram fish times 10 times, we don't know yet. You can kind of see the gravities actually factor out. That makes life a little bit easier. So 2 times 0.7 is 1.4 equals 3 times r3. And then we're going to divide by 3 on both sides. I'm left with r for the 3 kilogram fish is going to be close to 5, and so probably around 4.7 meters. Now, is that possible, do you think, for this situation? No, so I must have made a mistake because that's not even possible, right? Well, 1.4 divided by 3 is not 4.7, it's 0.47. So always look back at your answer and see if it makes logical sense. Because if it doesn't, unless the question has told you that these are not realistic numbers, you might be able to look and see that maybe you made a bit of an error. So there we go. We have that you need to hang it 0.47 meters away. Now we can look back and see, does it make sense that the 3 kilogram fish has to be closer to the fulcrum, right, than the 2 kilogram fish? It does make sense based on what we talked about before. If you have a lot of force, then you can have less distance from the axis of rotation to equal not so much force, having more distance from the axis of rotation. This is the whole premise behind how several different kinds of simple machines work, like wheels and axles and levers. They all sort of use the idea of what's called a equilibrium or a balance of torques. They have one long arm and one short arm, and the short arm pushes with more force than the long arm has to. So it makes doing some work easier because you can push on the long arm and have to exert less force. So I hope this video helps you understand some basics about torque, and you can go back now and kind of look at your notes and then complete the worksheet. I'll leave you with this one question. If I applied a force to one side of a sort of spinning, like hands of a clock, and there was no torque to balance it on the other side, what would happen when the object started to spin? So think back to kinematics and try to figure that out. Good luck.